Sure, yeah. So what I was working on for the last few years is an experiment called the nEXO experiment, which is a radioactive decay experiment looking for a decay that doesn't actually exist. We haven't seen it yet. It's hypothetical. But if we do see indications of this decay, then we learn stuff about neutrinos, which are these fundamental particles that are all over us and passing through us at any given moment.
Okay.
Yeah.
Let's start with first things first. What is a decay in this instance?
Sure. I mean, so you have a nucleus that starts off in some state. So in the same way that you have transitions between different states in atomic spectra. So if I have a fluorescent tube and it's emitting light, you're applying some energy, you're exciting those atoms, and that's a chemical process where the electrons are jumping between different energy levels. And the emission of that or the absorption of that is a transition between two different states. For nuclei, similar things happen, but you have transitions between protons and neutrons, and it's much higher energies that are being emitted. In this case, in the case where I'm thinking about, it's called double beta decay, where the nucleus converts two neutrons to two protons and emits two electrons all simultaneously. Those electrons have MeV scale energy, so like mega electron volts, but that's a detail you can skip over.
Okay.
And we just measure those electrons coming off because they're charged particles, and charged particles like to interact with matter.
Okay. And what are neutrinos?
So neutrinos are sort of like these very light, like less massive versions of electrons that don't have an electric charge. And that makes them really interesting to study because, for one, they're hard to detect, and two, they are also the only particle in the standard model, which is the table that collects all the fundamental particles that we know of so far, that only interact via the weak force.
Okay.
So
And how unique are neutrinos? Because in your dissertation you say they're fundamental, but they're also very hard to study.
yes. So in the sense, well, they're unique in the sense that everything else in the standard model that makes up matter, so all the fermions in the standard model are charged particles. So the techniques you use to detect them, like basically when a charged particle exists and it moves through a magnetic field, it bends. When it goes through something that it can be ionized, it ionizes. So that's why we talk about ionizing radiation a lot. And you can measure the effects of this ionization process.
Can you give an example?
Yeah, so for us, we're using liquid xenon as a medium. So xenon, the noble gas, we condense it into
Isn't
a
that
liquid.
54 on the periodic element?
Yes, it is element 54. And we have a bunch of liquid xenon, and essentially any charged particle that passes through the xenon ionizes it and causes it to glow, and it glow in a very specific way. And that's called scintillation light, and we measure that scintillation light as well as the kind of ionization track that's left behind. And combining those two things, you can reconstruct what type of nuclear decay happened.
Okay, so it sounds like you're studying particle physics, given how in depth you are with the specific particles right now.
Yeah, so it's pretty much the thesis, or my focus has been, I would say, particle astrophysics. It's been a mix of like three different fields. For example, this double beta decay process is a nuclear physics process, but we're exploring it to do particle physics experiments, so measurements that tell us about the particles themselves, in this case, neutrinos.
Okay. And can you give some people an idea of what your work actually consists of? Are you working in a lab that's like using lasers or whatever other techniques that I don't know of?
Yeah.
Or are you working computationally? Like what does your work look like actually?
So most of my work has been computational, but we also have a lab. I worked in the lab for a couple of years, but then have since had to narrow the scope of what I'm doing just to finish the PhD on time. But yeah, we have a lab. This is an experimental project. We're designing an experiment, and what I've been doing in my thesis anyway has been basically doing computational physics simulations of various processes in order to better design the experiment.
Okay.
And optimize for what we're trying to look for. Yeah.
What's the advantage with doing physics computationally?
Well, it's not necessarily an advantage. It's just there are rules in physics, right? So we know we can predict what would happen when a charged particle passes through various media. And once you embed that in some sort of simulation framework, you can build all sorts of detectors from your imagination and just simulate what they would look like for various processes. So what your end result would be. And that way, you don't have to build 100 different experiments
Right.
to do the same thing. You can simulate a bunch of them, optimize them for what you're actually trying to measure, and then just pick one and actually construct it.
Okay. And how new is, or how robust is computational physics compared to, let's say, last century?
Well, computation, it's a very broad term. So I'm specifically talking about like particle physics Monte Carlo, which is like a very small subset of the realm of computational physics. Because, there's computational physics. I'm not the right person to ask in terms of like people do material science and solve like basically Schrodinger equations, I think. I don't even know. And that's a many-body like quantum mechanics problem, and that's a very different simulation technique than what we do, which is essentially throwing random numbers, because the way we treat particles interacting is they have a probability of interaction every time they approach another particle with some given distance.
Okay.
Yeah.
And there's something that you mentioned earlier, which was charged particles.
Yeah.
Is it possible for a particle to not be charged?
Yeah, so neutrinos are uncharged.
Oh.
So as soon as they're born, they basically travel in a straight line, for as far as we can tell, forever, until they interact with another particle and somehow emit some charged particle in some process.
Okay.
And so what we actually can measure is the result of that.
Oh.
So we measure the charged particle that's emitted in the end, which you can either think of as the neutrino being converted into the other particle or as another particle being emitted.
Okay. And it is established that neutrinos go beyond the standard model. And I was wondering if you could... Yeah, go ahead.
Yeah, so it's not that neutrinos go beyond the standard model. It's that the fact that they have masses, it's not obvious how to account for that in the standard model.
Can you explain further?
Sure. So the way we think particles, fundamental particles, have their masses come about is through what's called the Higgs mechanism. And the Higgs mechanism, in short, is a way to kind of marry the left-handed and right-handed components of various fields.
Okay.
And when you do that, you actually intrinsically gain a mass for that particle based on how strongly it couples to the Higgs field. So it's like a three interaction term, where you have the Higgs and you have the right and left components of the fields, and they're all glued together. The neutrinos, only the left-handed components can interact with the weak force. The weak force completely breaks this left-right symmetry.
Okay.
And so you either have to admit a right-handed neutrino field, which we know we will not measure, at least through the weak force, and since it doesn't have an electric charge or doesn't interact through the strong force, there's nothing we can do to measure them. So you have to just hypothesize that these exist and then marry them to the left-handed components, and then you can get a mass this way. Or you have to think of some other mechanism to generate the neutrino masses.
Okay. And how important is symmetry in physics? And why is it important that neutrinos they're not anti-symmetric, but they don't work exactly with these symmetrical laws?
So, I mean, symmetries in physics, it's very important. They're very important. But what you're asking about is neutrinos right now?
Yeah.
So could you repeat that question? Because I got sidetracked there
No,
for
it's
a
okay.
second.
So obviously symmetry is extremely fundamental to physics, and you're saying neutrinos do not interact symmetrically, correct?
Yeah, but the types of symmetries we're thinking of are different, I think.
Okay.
So this kind of left-right-handedness symmetry is a discrete, it's kind of like a reflection in a mirror. But there are more, there are many continuous symmetries that are associated with conservation laws through this thing called know-this theorem, which is...
Know this theorem?
No, I wish it was know-this theorem. Know-theirs. So it's Emmy Know-there. She was a mathematician back in the early 1900s, wrote down this theorem that essentially shows that for symmetries of this mathematical object you can construct called the action of any physical system you can think about, any symmetries associated with the action have to be correspondingly associated with some conservation rule.
Okay.
So in that sense, symmetries are very important in physics, because if you notice a symmetry in your action, then you know that there has to be some mathematical object that is conserved throughout the processes that will occur in that system. Does that make sense?
Yeah, it does make sense. So what don't we actually understand about neutrinos then?
We don't understand how they have their masses. We know that they have masses, and we don't know what mechanism by which they generate them.
Okay. And what is a
That's
mass in this instance, actually?
Mass is kind of your resistance to motion, in a sense. So this is like, the way I'm thinking about it is inertial mass, but there's also gravitational mass. In, if you have this property, that's, if it's large enough, you end up bending, your space-time. But that's not neutrinos. Neutrinos are extremely light, and also all these fundamental particles are extremely light, that you can basically treat the space in which they're operating in as completely flat.
Right, like of the atoms themselves.
Yeah.
Yeah.
So mass in this sense is just like it's a tool that we can use to be able to show how like the dynamics of a system will evolve.
Okay.
From an inertial perspective. So something heavy will continue moving in a straight line if it's very heavy compared to a light thing that knocks it, for example.
Right.